For the longest time, the mantra in AI was go deeper. Just keep stacking more and more layers onto a neural network to make it smarter. But what if the real secret wasn't just depth, but width? Today, we're diving into the brilliant architecture that flipped the script, the Inception network, which you might also know as GoogLeNet. Okay, so picture this. You're an AI architect, and you're building a brand new deep neural network from scratch. At every single layer you add, you have to make a choice. A really critical choice about how that layer is going to see and process the data. And trust me, the choice you make has some massive consequences down the line. So what is this dilemma? Well, it's pretty simple. For any given layer you're building, what's the absolute best tool for the job? How do you pick the one perfect operation that's going to squeeze the most useful information out of your data? And you've got a ton of choices, right? Do you use a tiny 1x1 filter to pick up on really fine-grained tiny details? Or maybe a bigger 5x5 filter to spot larger, more abstract patterns? Should you even use a convolution layer to find features? Or would a pooling layer be better to kind of shrink things down and just summarize what's there? Making the right call is tough, and the wrong one, well, that can be a really costly mistake. This is where the designers of the Inception network had an absolute stroke of genius. They just looked at this whole problem and asked a totally different question. Why are we forcing ourselves to choose just one? What if we just let the network try all of them, all at once, and let it figure out what's important? And that why not all of them idea is really the heart and soul of what's called the Inception module. So let's crack this thing open and see how this deceptively simple idea creates an incredibly powerful and really elegant structure. Okay, so here's how it works. On the left, you've got your input data coming into the layer. Now, instead of being funneled down a single path, the Inception module does something pretty wild. It makes copies of the data and sends it down 4 different branches, all happening at the exact same time. And what are those 4 paths? Well, the network is doing a 1x1 convolution, a 3x3 convolution, a 5x5 convolution, and a max pooling operation. It's basically looking for features at a whole bunch of different scales simultaneously, from the tiniest little details to much bigger patterns, all from the very same piece of input data. And here is the truly brilliant part. After all 4 of those operations are done, the network doesn't have to pick a winner. It just takes all 4 of those different outputs and stacks them together side by side, kind of like stacking Lego blocks. This creates one brand new, super rich block of information that has features from every single scale. Just to put some real numbers on that, let's say the 1x1 path gives you an output with a depth of 64. The 3x3 path gives you 128, and the other 2 each give you 32. You literally just add them up. 64 plus 128 plus 32 plus 32, and you get a final combined output depth of 256. It's simple, it's powerful, and it's crazy effective. I mean, it sounds like the perfect solution, doesn't it? A network that can see everything at once. But this amazing approach had a hidden, and I mean absolutely massive catch. So the idea was fantastic, but the execution hit a major roadblock. This whole do everything at once approach turned out to be a computational nightmare. The cost of running all those operations, especially those big convolutions, was just astronomical. Just how bad was it? Get this. If we look at just the 5x5 convolution part of a single module, the number of calculations required was over 120 million. That's for one tiny piece of just one layer. You scale that up, and the whole network just becomes way too expensive to actually build and run. It just wasn't practical. So that's the big question, right? How do you keep this incredible multi-scale idea, but without completely destroying your computational budget? Well, the solution they came up with is, honestly, just as brilliant as the Inception idea itself. And the solution came from the most unlikely hero, the humble 1x1 convolution. I know, it sounds almost boring, right? But the way it's used here, it's a total masterstroke of efficiency. See, a 1x1 convolution, when used like this, is often called a bottleneck layer. Its main job here isn't really to find patterns in the image. It's to intelligently reduce the depth of the data. Think of it like taking a really thick book and squeezing it into a super thin pamphlet, but without losing the main story. So here's the trick. Before you do that super expensive 5x5 convolution, you first do a really cheap 1x1 convolution. This squeezes the input data and dramatically reduces its depth.
Then you apply the 5 by 5 convolution, but now you're applying it to that much, much smaller block of data. It's a simple two-step dance that changes absolutely everything.
So what's the actual payoff? Well, remember that terrifying 120 million operations from before? By adding that simple little squeeze step first, the total number of calculations plummets to just 12.4 million. You get the same result, but for a tiny fraction of the computational cost. I mean, just look at this chart. The impact is staggering. It's a nearly tenfold reduction in how much work the computer has to do. This one simple trick is what made the entire Inception architecture possible. It turned a beautiful theory into something you could actually build. Okay, so now that we have our super efficient and incredibly powerful building block, the Inception module, we can zoom out and see how these are all stacked together to create the full network, GoogLeNet. So the final GoogLeNet architecture is made by stacking 9 of these super smart Inception modules one after another. This creates a network that's 22 layers deep in total, and it has other clever tricks too, like these things called auxiliary classifiers that pop up midway through the network to give it some extra hints during training, which helps it learn much more effectively. When you really boil it down, the legacy of the Inception network is this huge shift in thinking. Instead of having a human architect try to guess the best design choices up front, this approach empowers the network to figure it out for itself by giving it a whole toolbox of options at every single step. So if you're going to remember one thing from all of this, let it be this. The Inception network gets its amazing performance by being able to look for information across all these different scales at once, and crucially, by doing it in an incredibly efficient way. It proved that sometimes the best path forward isn't to go deeper, but to go wider. This idea, this revolution of thinking wider, not just deeper, completely changed how we design neural networks. And it leaves us with a really fascinating question. What other fundamental assumptions are we making in AI right now that are just waiting for the next brilliant, counterintuitive idea to come along and shatter them?